In this video, we'll be introducing the concept of using simulation-based optimization with Simio. And we're going to start out with the serial manufacturing system model that we initially developed back in Module 3. So let me show you that model first and make sure we understand our starting point. And so if we run the model, you can see that we have 4 servers. And that we're using entity symbols that change as we progress through the manufacturing process. So the part arrives, goes to M1, and then switches symbols so that you can see different colors. In addition, we have reference properties that we use to specify the buffer capacities between the stations. So if I stop the model and then change my buffer capacities to say 232, for example, that's saying that I want to have the capacity of this buffer between M1 and M2 to be a value of 2, the capacity of the buffer between M2 and M3 to have a value of 3, and the capacity of buffer between M3 and M4 to have a value of 2. And the reason we don't need to capacitate the buffer here in front of station 1 is that we are trying to use this model to assess the capacity of the line. And one of the assumptions that we had was that there were continuous or an infinite number of parts available in front of M1. So whenever M1 is available, there was a part available. And so to do that, we used a on-event arrival mode. And so we essentially created our first part at time 0, and then every time a part exited the output node of M1, so it had space to move to M2, we triggered a new creation for M1. And so there's no need to have a buffer here because we're modeling infinite capacity. And so the 3 buffers of interest are between M1, M2, M2, M3, and M3, M4. So if we look at the experiment that we developed, again this was in lab 3, we see our controls for our 3 buffers, and our responses of interest were the utilization of our 4 stations, the number of parts in the system, the time a part spends in the system, and finally throughput. And we measured throughput as the rate that parts depart the system, and so we created a response by the number of parts that enter the input buffer of the sink divided by the runtime minus the warm-up period. And so then we defined several different scenarios by sequentially incrementing the number of or the buffer configuration. So buffer configuration is how many buffer slots I assign to each one of the buffers. And so one of the tasks that we had in Module 3 was to select the best allocation of buffer slots. And I used 10 here. I think we used 20 in the previous lab. 10 is going to make our process go just a little bit faster, but we could apply the exact same process if we wanted to use our 20 buffer slots. Okay, so the first thing we had to do in order to define best was specify what our objective was. And so for this model, we're defined best using the throughput measure that we defined as our response. So the rate at which parts depart the system is defined as throughput, and our objective is to maximize that throughput. So from an optimization perspective, our problem now is to maximize the throughput subject to a constraint on our 3 decision variables. So B2, B3, and B4 are the decision variables, the buffer the buffer capacities, and we have a constraint saying that we want to allocate these such that the maximum or the total number allocated is not more than 10. Now, in order to simplify our process, I'm going to use some additional knowledge about how the system works and incorporate 3 additional constraints, saying that I want to just investigate the scenarios where we have at least 2 and less than or equal to 4 buffer slots for each one of our locations. And so again, adding these 3 constraints really just makes the problem a little bit easier to solve so that it won't take so long to run the optimization. If I had no information, in other words, if I didn't know that the optimal solution was within the space, I would simply not include these 3 constraints, and I would let the process itself select the best optimization amongst all possible configurations. And so within Simio, the basic process that we're going to follow involves 3 steps, or usually involves 3 steps. The first thing we're going to do is we're going to use a Simio add-in called Opcode to create our initial experiment. Create and run our initial experiment. Then we'll use the subset selection tool to identify potential candidates, to identify candidate solutions. And finally, we'll use another add-in, select the best scenario using KN, to identify the best from among our candidate solutions. So let's get started with our Simio model. So we'll pull our model back up. And I want to first make a couple of little simple changes. The first thing I want to do is we had a runtime of 125 hours with a warm-up time of 25 hours. I want to change this to run a little bit longer, so I'm going to run for 300 hours and run a warm-up of 100 hours, so we get a little bit longer runtime in our experiment. Okay, so the next thing that we're going to do is we have throughput is our primary objective. So I'm going to select the experiment properties again and then change this primary response value from utilization of M1, which was the first response we created. That's how it was selected as the primary. And I'm going to change my response to throughput. And then secondly, I'm going to go to the throughput response and select an objective, and we want to maximize. So now we've set the primary objective for our experiment, or the primary response for our experiment, and then we've set an objective to maximize that value. And the next step is to select the Opcode add-in. So I'm going to go to the Select Add-in on the ribbon, and you can see the 2 add-ins that come by default. There's Opcode, and then, as I mentioned before, we will then be using Select the Best Scenario with KN at the third part of the process. So I'm going to select Opcode for Simio, and we get the warning saying that an experiment cannot be undone, and that the undo history will be cleared, and so we won't be able to undo things from this point forward. So I'm going to just say yes, and then we see that when we look at the experiment properties, we have Opcode for Simio parameters. So there are special parameters associated with the Opcode add-in. And so I'm going to change a couple of these. I'm going to change the minimum number of replications to 10 and the maximum number of replications to 30, because we have a fairly, the differentiation between the buffer allocation is fairly small, so I want to run for a few more replications at minimum in order to identify the good configurations. The other thing I want to change is the relative error, which specifies the, as we see here, the confidence level expressed as a percent of the mean. So instead of the default 10% of the mean, I want to have the relative error be 5% of the mean. We have the confidence level. We'll just leave that at its default value of 95%. And finally, our objective type is single objective, because we're interested only in the throughput value. And so from the Opcode parameter standpoint, we've set the min and max number of replications, the maximum number of scenarios that it will experiment with, the confidence level, and then the relative error, and then we determine whether it's single or multi-objective. For this problem, we're going to stick with single objective. So we have our objective defined. We have set to maximize throughput, and now the next step is to implement our constraints. And so we have basically, in Simio terms, we have 2 types of constraints. We have limits on our controls, B2, B3, and B4, and then we have a constraint that's expressed in terms of those control values. So let's look at how to implement those. And we'll start out with the control constraints. And so when we select an individual control, you can see that we have a couple of additional parameters associated with Opcode. First of all, we want to include it in the optimization, and then we specify the minimum and maximum value and the increment. And so we set in our, as our constraint, we want the minimum to be 2, the maximum to be 4, and we'll leave the increment at 1. And so what Opcode will do is include all possible values, so 2, 3, and 4, as candidates. So we will do the same thing for buffer 3. So between 2 and 4, and buffer 4, yes, between 2 and 4. So by setting the limits on the controls, we've implemented our first set of constraints. Now our total capacity constraint, we need to add a constraint. So I'm going to go to the ribbon and add a constraint. And our expression that we want to constrain is simply buff2 plus buff3 plus buff4. And the lower bound on this constraint is we have a minimum for each one of our control values of 2. So the minimum value is going to be 6. And the upper bound is going to be 10. And so you can see immediately what happens is from our previous scenarios that we defined in the last experiment, we have a number of the scenarios that are colored red, meaning they're infeasible. So since we added a constraint and we have existing scenarios, S1 or S0 and S1 violate the constraint on the lower side, that total value is less than 6, and scenarios S4 through S500 violate the constraint on the upper bound. And the only two scenarios that meet our constraints are S2 and S3. So now we have our optimization completely defined. We have the objective defined through our OpQuest parameters. We have our 4 constraints, the 3 control limits, and the 1 proper constraint. And so now we're ready to go. So we go back to Simio, and again I've already selected OpQuest for Simio, and so when I click Run, again I get the message saying that my undo history will be removed, and then all of the previously defined scenarios disappear. And now Simio, or OpQuest, the add-in, has complete control over the creation and running of the experiment. So based on the parameters I've given for OpQuest, it's making the determination of what values to set for the individual controls and how many replications to run, subject to our constraint of minimum or maximum. And so we will pause now and let OpQuest run, and then we'll restart once the OpQuest has completed its initial run. So now we can see that OpQuest is completed, and if we scroll down we can see that it ran 23 scenarios, and in this particular case it ran all the possible scenarios. So we had three different decision variables, each have 3 possible values. So we had 27 total scenarios, and then our constraint that limited the maximum removed 4 possible configurations. So what OpQuest did in this case is it ran all the possible configurations. It doesn't always do that, but we designed a relatively small solution space so that we could do the optimization in a reasonable amount of time just for the video. So the next thing I'm going to do is I'm going to look at my throughput and sort the values based on throughput, so descending values of throughput. And we can now see that the solution 343 has the best, or it appears to have the best throughput. But remember, because we have stochastic components, these values are all sampled. So we don't know with certainty what these values are. And so if we go to the response results and look at our throughput, again we can see with our confidence intervals that we're not sure amongst several of these which one is in fact the best. In fact, it's not clear whether we've run enough replications in order to identify the best possible solution. So there's been a considerable amount of research recently to develop statistically valid methods to select the solutions that are potentially the best, or to identify the best solution. And there's a general process called ranking and selection that's used to do that. And so the subset selection procedure within Simio implements one of those techniques. So if we select our throughput and then click on subset selection, what Simio does is identifies or partitions the solutions into 2 possible sets. There's a set of possibly the best and a set that we can reject. So when we select subset selection, Simio identifies scenarios 19, 4, 17, 3, and 8 as all being potentially the best solution, and the remainder as not being not necessary for us to continue further exploration. So as just a note, if you remember when we first did the Simio add-in, we modified the replication parameters and set the minimum number to 10 and the maximum number to 5. In fact, we did that because if we used the default of 5 replications for the minimum, then the subset selection procedure would turn out to be unable to select the best. Statistically, we didn't have enough replications for it to make its partitioning. So I increased that to 10 so that we could see this. So at this point, we have the possible solutions, and we now need to do further exploration so that we can differentiate between these candidate solutions. So what we're going to do is we're going to deselect and then just select those scenarios that are in the set potentially the best. And then finally, I'm going to use the second add-in that we mentioned, which is the select best scenario using the Kim-Nelson procedure. Again, I get the message saying I can't undo this. And then we have to set another parameter, a single parameter here, for the Kn. We have the confidence level before, we have a maximum number of replications, and now we have something called the indifferent zone. And if we look, the indifferent zone tells us what the smallest meaningful difference is for identifying the best. So when I look at these two values, again, we're doing a sampling procedure, and so I want to say what's the smallest value that would identify these as different. So we're going to set this equal to 0.1, saying that 45.7 and 45.6 would be considered different. So I set those values, and now I click Run, and again, I can't undo. So then Simio runs, and now the second add-in, the Kn, is going to run until one of two things happens. It identifies the best or exceeds the maximum number of replication. And so it stopped, and so I will go back and sort descending, and now we see that only the single scenario 19 is selected, and so the procedure has identified the configuration 343 as being the best configuration. And if you've worked with the buffer allocation problem very much, you probably knew before we started that this was in fact going to turn out to be the optimal solution. So recapping what we did, we took a model that we had previously developed, and the model was designed to have 3 controls, and then we created an optimization problem using the controls as our decision variables, and we used the basic procedure to let Opquest create and run the initial experiment. Then subset selection identified candidates that were potentially the best, and then select the best scenario add-in to identify the best from among those that the subset selection identified.